Dear viewers, let us today have a discussion about the De Morgan's theorem and its verification. Well, as per the De Morgan's theorem, there are basically two laws. One is, in a simpler terms, we can say that the NOR logic is equivalent to AND logic with inverted inputs. That means bubbled AND inputs or a bubbled AND gate. And on the simple terms, if you talk about the other one, it is the NAND logic, which is equivalent to OR logic with inverted inputs. So, in the first one, you can see we have A or B whole bar is equal to A bar and B bar. Similarly, for the next one, we have A and B whole bar is equal to A bar or B bar. So let's have a look at the first one where we are saying NOR logic is equivalent to AND logic with inverted inputs. Let us assume Y1 as A or B whole bar. So from this we can see we have a NOR gate having two inputs A and B, and the output is A or B whole bar. What we have to do is we have to prove left hand side is equal to right hand side. So what we are doing is we are considering the left hand side as Y1 and the right hand side as Y2. And in case of Y2, we have the inverted AND gate, inverted input AND gate, where the inputs are bubbled, and we can see the output is A bar dot B bar. That's A bar and B bar. So let's see whether Y1 is equal to Y2 or not. So this is the circuit, this is the logical circuit representation. Here we'll be using all basic gates, that is AND gate, NOT gate and a OR gate, to see whether Y1 or Y2 are same or not. Okay, so to implement A or B whole bar, what we are doing is we have a OR gate which is having two inputs A and B, and the output is A or B, that is here, and we have to complement that using a NOT gate, and then we get A or B whole bar. Similarly, A and B are put into the AND gate via these two NOT gates. So A will get inverted as A bar, B will get inverted as B bar, and at the output we will get A bar or B bar. So we are considering two outputs. This is Y1 and this is Y2. To prove the first law, we just have to show that Y1 is equal to Y2. So let's take or let's try to analyze all the combinations and see whether the outputs are same or not. So let us first apply a zero logic to both the inputs. Here we can see we have applied 0 0. So we all know that when the input of OR gate is 0, the output will be 0. So this will get inverted and will get a 1 at the output of the NOT gate. So we have recorded a high under Y1 corresponding to the combination A equal to 0, B equal to 0. Similarly, when both the inputs are 0, this will get complemented by the NOT gates and will get a high at the input of the AND gate. And we all know it is the only combination when given at the input of the AND gate, the output becomes high. So here Y2 is high. Now let's try to understand the next combination where A is 0, B is 1, A is 0, B is 1, obviously any one of the input, if it is high, the output of the OR gate will be high, and obviously it will get complemented and we get a 0 at y1. We will record that here. Similarly, when a 0 is there at A bar is 1. Similarly, B is 1, B bar is 0. So any one of the input, if it is 0, in the AND gate, then the output of the AND gate will be low. So we'll get a low. So again, we can see both are same, y1 and y2 are same. Now let's have the other combination. This again makes the output of the OR gate 1, the NOT gate as 0, and then again here we can see the input of the AND gate, one of the input is 0, so output will be 0. So again we see in this particular combination, the outputs y1 and y2 are again same. Now the last combination where both the inputs are 1, when both the inputs are 1, obviously the output of the OR gate will be 1 and NOT gate will be 0. And in this case, the inputs of the NAND gate, inputs of the AND gate are 0. Correspondingly, the output will be 0. And hence, the last combination we can see both the outputs are again 0. So this shows that the output is nothing but the truth table of a NOR gate, but both the outputs are same, and hence we can say that the NOR logic is equal to the AND logic with inverted inputs. Now let's move on to the next one where we have the NAND logic, which is equivalent to OR logic with inverted inputs. Again, we will consider A dot B whole bar as Y1 and Y2 as A bar or B bar. And from this diagram we can see this is the representation of a NAND gate, and this is the representation of a bubbled OR gate. Now let's see the circuit diagram, and in the previous circuit diagram and the present logical circuit diagram, we can see we have just interchanged the AND gate with the OR gate. So if you make the circuit on a breadboard, all the connections remains the same. You just have to take out the AND IC, replace with the OR IC, and replace the position of the AND gate with the OR IC. So in the circuit we can see that the first combination is 0 0. So when we are applying 0 0 at the input of the AND gate, obviously the output will be 0. Any one of the input, if it is 0 at the input of the AND gate, the output will definitely be 0, and it gets complemented by the NOT gate and we get a 1. So 1 is recorded here. Similarly, the output of both the NOT gates are 1, which is entering the OR gate, and the output will be 1. So here we can see both the outputs are equal. Now let's move on to the next combination. We have a 0 1, 0 at A and B is at 1. So the output of the AND gate will be 0 since one of the input is 0, and then the complemented output will be 1. Similarly, input of the OR gate will be 1 0 since one of the input is 1, so the output will definitely be 1. So again here we can see the combination 0 1, the output both are at high logic. Let's see the other one. When A is 1 and B is 0, the output will be 0 of the AND gate, and similarly the complemented output would be 1, and both the inputs to the OR gate is 0 and 1. One of the input is 1, so the output will be 1. So in this case again in the combination where A is 1 and B is 0, both the outputs are at high logic and are same. And let's see the last one. When both the inputs are 1, it is the only condition when the output of the AND gate is 1, and obviously the complemented output would be 0. And since both the inputs A and B are 1, the complemented uh, inputs to the OR will be 0, and it is the only situation when the output of the OR gate becomes a 0. We get a 0. So from here we can see that both the outputs are same for this combination. So all the 4 combinations of this particular circuit shows that the output Y1 and Y2 are same. So we can say that the law 2 stands. Thank you very much for watching this video. Stay tuned for other videos on digital electronics. Thank you. Thank you very much.